for it. I'm going to use the, I wanted to make some changes to the presentation after teaching the non-honors class. I'm going to show you their class. It's the same class, just different homework. Do you have the homework copy down from yesterday?
Yes.
Okay, so I'm not going to show you the homework slide. What?
My sneeze, I got some blood out.
Well, you're welcome to Colorado,
I think I'm probably gonna have
the land of the bloody noses.
stop bleeding right now.
Well, put some pressure on it.
Nope. Oh well.
All right, Ben, I started a little bit late because we were going over the answers to the quiz. Have you taken your quiz yet? No, I had it on mute, sorry. One more time, Ben. Did you take your quiz yet? Ben is being silent. He's probably away from the screen.
I wish I could walk away from it.
I have it set to automatically allow people in, so. All right. So when he gets on, somebody remind me to tell him that we're looking at not his class slides, but the other ones. All right. Where did we leave off?
We left off on box 4, I think with theorem 3.
We did box 5? Okay.
Oh, we did do box 5? Oh, yeah.
Hello.
All right. Ben, we were going over the quiz. Have you taken your quiz yet?
No, I'll do that some other time.
I didn't want to record that, so.
Okay.
All right. At quick review, remember we're talking about polygons. Our first polygon, the triangle. Remember, polygons are made up of segments joined at their endpoints on a flat plane, and they're also closed. A triangle is hard to make unless it's closed. But as long as you join them at the endpoints, you do in fact get a shape, a recognizable shape. The first one is a triangle. I don't think I said it, at least in this class, but I know I said it last year. Polygon, what do you notice? Polygon?
There are polygons. There's multiple gons.
Multiple gons. Gon is I don't know if it's Greek or Latin, but it means angle or corner, right? So many angles, many corners. And then we call those angles or those corners the vertex, or for singular, vertices for plural, and we name triangles with the triangle shape. And then you pick any letter to start with, and you have to go clockwise or counterclockwise. You got to say all the letters. All right. The 3 ways to classify triangles by their sides. McKinley, go.
There's the no size ceiling triangle, isolate triangle, equivalent triangle. I'm pretty sure I said all of those wrong.
One more time.
Ceiling triangle.
Scaling.
Icicle triangle.
Very nice.
And equivalent.
Yes, 100% correct. So scaling, icicle, and what are we going to call this one?
Equivalent.
Oh, now we're saying it right. Equilateral. So scaling, isosceles, and equilateral. All right, Jack, by angle measurements.
What do you mean?
Well, how do we classify triangles by angles?
Oh, right, acute, obtuse, and equilateral angular.
Equal angular. All right. So we get 3 for sides. We get 4 for angles. Okay. And then I introduced you. This was new, and it's an auxiliary something. In this case, an auxiliary line is what I'll use. But you can put points wherever you want them, right? You can create new angles if you wanted to. The issue with making angles is it's kind of iffy because you got to be 100% accurate. For instance, we could, if I drew that right there, I could extend this and make a new angle. We could say that those two are vertical. I could do that, right? These would be auxiliary lines, not auxiliary vertical angles. But you can't say something like this angle right here, and then over here draw this angle and say like this one is something weird without knowing what this angle is here. Now you could make one that's congruent. You could do that, right? But you can't just make some claim without some proof behind it.
So then how would you be able to say that
2 angles are parallel.
Well,
angles
not
wouldn't be parallel.
Lines connected are 2 angles. Like you couldn't say that. Like if you for example, if we need to prove something that we've learned in this chapter, alternate interior
Right.
angles could solve proof for us. How are we to say if we're adding a line that's
I'll give you a better description.
Parallel.
Let's say we had this shape, which we haven't talked about yet, and that we're told that this angle is 65 degrees. I can't label this angle right here 65. I can't make that claim.
Well,
Yes,
it's not
you can.
65.
It can't
Right.
be.
Well, clearly it's not. But I'm saying I can't make any. I said you can literally make new lines. You can make new angles.
But
You
you
can
can
make
make the
things
bottom
congruent.
one 65. because
What
it's
I could
parallel.
do is I could make an angle over here that is absolutely congruent to that one, and I can make an angle over here that is absolutely congruent. I can do that.
Or you could make it. I know how to solve that. So you could make a line that's going out from one of the plates.
I can absolutely do that.
So, like a line from there, and then you have a line.
Well,
from
that's
there.
clearly going to be 65.
And then you know that those two are supplementary. So then you can see that that one is the other one.
Supplementary?
Yeah, supplementary.
Oh, you mean this angle?
No, that angle and the one on the top next to
Oh, and that one, yeah, that's absolutely
And
supplementary,
then
sure.
you can use alternate
And by the way, we will
material.
use something like that this year as well, too.
You could also
Yeah, and
say
then
that
you
the
could-
one that you drew is corresponding to the one that's
Well, alternate-
Only if I made things parallel, right?
Yeah, so
Only
if
if I made them
If
parallel.
those are parallel, then you could prove that
Yeah.
easily just by adding that angle and then
Yeah.
saying alternate interior angle.
Yeah, so for instance, if I extended this right here, then I could say, and these two are parallel, I could say that that's parallel, that absolutely. Okay. All right. Okay, so we will use auxiliary lines, auxiliary points, throughout I don't think we ever draw an extra angle, but we will do auxiliary lines and points. All right, and then remember we did prove this. Well, I'm not going to go through the proof again, but just remember the sum of the interior angles of any triangle is 180. I know I've told this class this before, but this is I absolutely have to throw this in there. On the Earth, right? You're on the Earth and you're standing on the equator right here. And you turn 90 degrees to your left or right. We'll just say you're facing this way. You turn left and you walk straight. And you don't stop until you're on the top of the world. And I said you turn 90 degrees. Where are you?
The middle of Antarctica.
No,
Antarctica's down here.
You're in space. You're
No, I'm on the Earth. I'm walking.
You're
I'm
in the
walking.
North Pole, in the middle of the North
I'm on the
Pole.
North Pole, right? Now I go back to my starting point. I walk 1,000 miles due east, and I do the same thing. I turn left 90 degrees and walk straight. Guess what you made? Guess what shape you just made?
Triangle.
I did make a triangle. But what's the problem with that triangle?
It's not really. It's impossible to make that
Well,
triangle.
I just made a triangle, literally.
But it's
Well,
impossible
the
because
two
no
sides-
one
because
walks
it's a
straight. There's an
circle,
ocean.
it's not a proper.
What's the problem with these two things right here?
You can't because it's a circle.
They're both 90.
They're both 90 degrees. I'm claiming I made a triangle. I did.
It's because it's a 2D drawing and
Yeah, the problem is that-
The problem is the lines go like this.
Agreed, but when I walk in a straight line, am I not walking in a straight line?
You are, but that's like the same way all lines are circles.
Right.
If you draw a line exactly in that direction, it becomes.
So the issue with this one, and by the way, this is real life. I mean, this is not a made-up triangle. It's a real triangle. Problem is the triangle is on the Earth and it's curved surface. We call this type of geometry spherical geometry. So clearly in spherical geometry, what can you tell me about triangles? What's the sum of the interior angles of a triangle on a spherical object?
more than 100.
More than 180. It gets weird, right? But we are dealing this year with what's called planar geometry. It's only geometry on the plane. The irony there is I'm teaching you geometry, the measurement of Earth, and we're not going to do these measurements on Earth. We're going to do it on a flat surface. So almost none of the geometry that I will teach you actually is useful when we talk about like navigation. Like you get in an airplane and you want to fly to New York, don't use the geometry I'm teaching you. You're going to wind up in the wrong spot. Ancient mariners figured this out a long time, that all the geometry the Greeks were teaching them, as soon as they started going off in a direction, they're like, wait a minute, this doesn't work. I wound up in the wrong spot. What's happening here? It's because they were trying to do two-dimensional geometry on a three-dimensional shape. Okay, so that's my side note for that. Oh, by the way, we define a line in plane geometry as what?
Straight line. All lines are curves in the world.
No, okay, let me finish the statement. We define lines in plane geometry as what?
Straight, they go in straight.
We don't even say straight, we say opposite directions forever. Do they ever touch each other?
No.
Never.
But they do touch each
But
other.
on a
the air.
spherical object, lines are actually circles, like the equator. That's a line. So lines actually intersect each other in spherical geometry. That's kind of weird. All right, so the proof was, we drew that auxiliary line. We did some labeling, which we're allowed to do. And by the way, this is really speeds things up. Instead of having to name it angle DBA, we can just say angle 4. It just helps us a lot. We showed that 4 plus 2 plus 5 is 180. We showed that 4 is congruent to 1 and 5 is congruent to 3 because they're alternate interior angles, because we made the auxiliary line parallel to AC. We put those two statements together, those two right there.
Of course, you have to say that DB is parallel to AC, right?
I did, and that
Oh,
was
you
my
already did,
construction.
you already
Yeah, that was my construction. And then therefore we showed. This is the one little step that you will forget if you're going to forget a step. You would really like to do a substitution immediately with this statement and this statement, but you can't because this one says measure and this one says congruency. So somewhere in there you have to change one of them back to measurement so that you can wind up your last statement. Okay, so that's where we kind of stopped there. This was Theorem 311, which states that the sum of the interior angles of any triangle, at least in plane geometry, is 180 degrees. Corollaries, I describe those as leaves on a tree. So if our tree is the sum of the interior angles is equal to 180, the rest of those 4 corollaries we're about to talk about come specifically from this theorem right here. Right? All right, so we did do this or we didn't do this one?
We did do this.
Okay, so here's all this says. It says that 2 angles of one triangle are congruent to 2 angles of another one, then the third ones are congruent to each other.
Yes, but you don't need to do a proof on that. It's
It is kind of obvious, isn't it? All right. The technique was, well, you show that, well, these 2 are congruent to that one. The sum of these add up to 180. The sum of the second one add up to 180. Now we have 2 statements that equal 180.
So saying that by one angle in the same place, you know the triangles are congruent. So if you say that 2 is congruent to 5, and
You know that, what was your last statement?
if 2 is congruent to 5, then you know that the triangles are congruent.
That's not true.
Why not? Well, knowing that they're in the same position on the triangle.
Are those 2 triangles congruent?
No. Oh, yeah, you're right.
Even though these angles might be exactly the same, these are not congruent.
Yeah.
We're going to spend a lot of time in this later on in the book. These are called what kind of triangles? Anybody know? When the angles are the same, but the sides are not the same, we call them
different angles.
Call them similar triangles.
Similar triangles.
But we will talk about, ooh, that's a hard chapter. That's probably one of the hardest chapters in the book, the similar triangles. All right. Okay, so that was Corollary 1 to Theorem 311. You wrote this down, yes or no?
Yes.
No? All right. Oh,
No, we wrote it down.
well, Anna's shaking her head no.
And I have corollary 2.
Yeah, we got 1, 2, 3, 4. And then we got the last theorem.
So if the ocean is blue, then why is land green?
Because there's grass that goes in the earth.
Have you heard what's called a non sequitur?
No.
Okay. Hey Siri. Hey Siri. What? Why does it never work when I want it to work? Hey Siri, what is the definition of a non sequitur? She's not saying anything.
Non sequitur means a conclusion or statement that does not logically follow from the previous argument or statement.
What did you say? If the sea is blue, why is the grass green or something like that? Because one doesn't have anything to do with the other one. It's called a non sequitur.
Oh, yeah. It's like saying one line goes on forever. Why doesn't the other line go on? Why doesn't the second go on forever?
Well, there might be something. It's like saying, well, I have 2 sisters, right? Why isn't my uncle named Bob? It's a non sequitur.
But
One
why
doesn't have anything to do with the
go
other
on
one.
forever? Why do they need to go on forever? What purpose does that serve them?
Okay, I'll allow you to think about that right before you fall asleep tonight. All right, so Corollary 2 to Theorem 11 says, take a guess.
That all angles are congruent and then it's an equilateral triangle.
Why? Prove it.
Because it's an equal angular triangle.
Prove it. Not to prove that it's equal angular, but prove that those are equal to 60.
Why? Oh, well, if B is congruent to C, then C must be
No,
congruent.
no, that's the definition of equal angular.
Yeah, okay.
Prove it's 60, though.
I can't if you don't give me any numbers. What do you mean? So you're saying from this diagram, prove that it's 60?
Prove that an equal angular triangle, the angle measurements are 60. Prove it.
Because they have to be 60.
Prove it.
60 plus 60 plus 60 equals 180. Nothing else equals 180.
Okay, that's the proof. I might have done it a little bit different. I might have said that, well, the sum of the interior angles is equal to 180. There's 3 of them. They're all congruent. That's the definition of equiangulars. All the angles are congruent, and 180 divided by 3 is 60. Okay. Yeah, you just did a proof, and that's why you don't do this one for homework. It's some corollaries are far more interesting to prove, but this one isn't. That one's easy. Do you agree with? You buy the proof?
Mm-hmm.
Okay. So write that one down. Each angle of an equiangular triangle is 60 degrees. I almost said equilateral, but guess what? An equilateral triangle is an equiangular triangle. We have to prove that one.
Yeah, that's what I was saying earlier.
We got to prove that, but we will.
That has to be.
We'll prove it.
You can't shrink one another without making it a nice
All right,
sausage.
we'll prove it.
You can shrink that. What if you shrink that?
Then we get a
smaller?
similar triangle.
But if you shrink it more and more, it's gonna not be 60 degrees anymore.
Oh no, it will always be 60 degrees.
Wait, it will be, but the measurements will never be the same.
Um,
if you keep on shrinking
Did we
it.
do dilations in pre-algebra?
No.
So if we dilate this, make it bigger, make it smaller, not about the center of the shape, but out one of the corners, then you will distort things. But if we dilate it, make it bigger or smaller, about its middle part right here, then everything grows at the same rate or shrinks at the same rate. And so you maintain 60 degrees. We good? All right, I said there was 4 of them. Okay, what am I saying here? So here's what I'm saying here.
But 9 that they're different. One's obtuse and one's
If you have a
right angle,
right triangle,
right triangle,
how many 90-degree angles can you have?
one.
Why? Prove it.
Because there's
you
only
can't
one
have
90 degrees. If it's
Prove
too-
it.
If it's
Because
too small or too
If there's
big, it'll
two
be
90
different.
degrees, it's more than 180 because you have
It's
3
not-
angles.
Okay, I'll buy that. I'll buy that. You gonna say something else? You know what I mean?
Well, I'm saying that if you have it, if it goes bigger than 90 degrees, then it's obtuse. It's too big to be 90. If
So
it
you
goes
can't.
smaller,
You
it's
certainly
obtuse.
can't on a right triangle. You can't have a.
You can't have an obtuse.
No, you said it right the first time.
Oh, you can't have an obtuse.
You
or-
can't have an obtuse angle on a right triangle.
So you have to have 245.
So you have to have 2 acute angles,
Yes.
Or 245-degree angles.
or they can be congruent. They can't or not. It's up to the particular triangle. They both must be acute. And what am I going to say here?
You can only have one of 2 things.
You can only have one obtuse. Prove it.
Because if you have another one, then you go over 180.
Yeah, you go.
No.
You go.
Yeah.
over
If this is 120, this one could be 1 degree.
Well, no. What I'm saying is if you have another obtuse angle, then it goes over.
Or another.
Acute.
Another right angle.
Right. So that's all theorem, and I'll accept that as proof. That's all that Corollary 3 of 311 says. It says in a triangle, there can be at most 1 right angle or at most 1 obtuse angle. You can't have what?
That's what we're doing.
We're going to do another one, which is pretty nifty. The last theorem is pretty neat, and we're going to use it a lot too this year.
I feel like we've been saying that a lot. We're going to be
Because-
using this one a lot. We're going to be using there has to be some
All
that
right.
we're never going to see again.
What is today? Today is September the 17th. Ask me December 17th if we're actually here. We'll revisit this, and you tell me. You'll be able to confirm or deny whether we used the things that I said. So I said we were going to use vertical angles a lot.
CDCMC or something like that.
Oh God, we're going to use that one. I don't even have to prove that one to you. And I'm going to say that we're going to use the next theorem, what was one after this next corollary. We're going to use that one a lot. But vertical angles, linear pair, we use that a lot. We good?
Math class. Yay.
All right, Ben, you good?
I think Ben lost contact or alien squids are attacking his house.
Michaela, you didn't notice anything about your quiz?
I got a B out of it.
You
Yes,
didn't
I did
notice
see that.
anything about your quiz?
Yes, you printed a picture on it. Of
Okay.
some,
I saw that when I was looking over. I was like, what the?
That wasn't on my quiz, was it?
I was like, why is that not on
I got tired of him. I tried to pick the creepiest octopus thing I could find on the internet. And there was some pretty weird stuff that I couldn't print. All right, don't you Google that. All right. Okay, last one. Guess what I'm going to say?
A corollary 4.
Corollary.
A corollary 4 is related to theorem 311. Then it must be true and x and y are bigger than 9 or 9 are obtuse
Add
together.
X and
What
Y
am I going
out
to say?
of
Are you looking at your book? Okay, you can't talk. Look at the picture and tell me, take a guess
X
what I
and
will
Y
say.
together can equal 180.
You're pretty darn close.
90.
90.
Say it
it's
again?
Equal,
X
What?
and Y together equal 90.
That's what this one says.
but
Okay?
no, but actually,
But
yeah.
what kind of triangle must it be?
All right, I'm trying.
So if you have a right triangle, the other two angles are,
Add up to 90 degrees.
we have a word for that.
The sum of 90 degrees.
We have a word for that. Complementary.
Oh, right.
Boom, math genius.
Yeah, you did. I didn't tell you. I just said, look at the picture. Tell me what I'm going to say. That was good.
That's me.
They were saying
I
it
helped.
way before you guys were,
Well, I didn't have any time to say it.
even though Allie looked at her book. You can look at, I don't care if you look at your book.
Allie, how could you look at the book? How could you do that?
Well, I'll just say all the theorems and corollary, I don't change any. I might change the picture slightly, but I won't change the words or something. I'll put it exactly like what's in the book. I typically add something at the bottom because the book doesn't put this. They'll just make the statement. Right? We will use this one enough, right? That if they give you, it's a right angle, the other two add up to 90. All right, let's look at this picture. This shape appears a lot in our geometry book. I call it the hourglass shape. Wait, is P congruent to V?
What?
Yeah.
Yes, congruent.
All right, period 2 struggled mightily at this. Let's see if you really are an honors class. So McKinley, here's what I'm going to say the thing I said to them. I want you to look at the picture and tell me anything that's true, whether it helps us or not.
Wait, we don't have a given.
Well, the picture's the given.
Okay.
Look at the picture and tell me anything that's true.
All right, P and V are congruent. But
No, that's what we're trying to prove.
R and E are
Which one?
congruent. R and E.
Why?
Because they add up to the same measurement.
Why?
Because of congruent angles.
That's a little angle.
Why
That's
on the
little
picture? Why on the picture? Can you say that? It's true, by the way.
Because of
Look at the picture. Don't look at your book. Look at the picture. Why are R and E congruent?
because they are congruent.
Why?
Because the two triangles are the exact same.
You don't know that.
Yes, they
Clearly,
are.
that one doesn't look like that.
It's just smaller than the other.
You're overthinking this. Why is R the same as E? And this is what period 1 had a problem. Period 2 had a problem as well.
The lines,
What do you mean the lines?
that could go right there.
What? Okay, those aren't lines. Those are arcs.
Yeah, those little arcs.
That's the reason why. Because it's indicated on the picture. Those arcs mean anything with one arc is congruent to anything else with an arc. Do you get that from the picture? So we could immediately say that R is congruent to E. Yeah? All right, Anna, give me something else you see from the picture.
Angle 1 is vertical to angle 2.
So therefore they must be,
Congruent.
okay. So that's also part of the given. Vertical angles are congruent. Okay.
Are we doing another proof?
We are doing a proof, but I didn't put it in the form of a proof. Okay. So why is P congruent to V? Oh, by the way, that's all you need right there.
Because you can substitute 1 and 2 with P and V, and it would.
No.
Yes, but you can substitute.
No.
Okay. P and V equal each other. Equal.
Take your magic hand,
Oh, I know what it is. Well,
and if you have your book open, flip back, or your book of truth, you might have to flip anything. Look at what we have. Look at the corollaries. 1, 2, 3, 4.
2 is obtuse, and B must be. 1 and 2 are obtuse.
You can't tell if anything's obtuse or cute from the picture. Can't tell that.
Well, everything on equal right? No, wait, that's not equal radical triangle. It's a no, maybe, probably not. I don't
Look
know.
at your corollaries.
And one is congruent to the other.
What does corollary 1 say?
If two angles of one triangle are congruent to two angles of another triangle, then the third angle is congruent.
Oh, yeah.
Oh, okay.
I eventually I got someone else in period 2 to do it, ignore that and do it a different way. Could it be done a different way?
Yeah.
I thought it was pretty cool proof, and I didn't even tell them. They came up. Give me another way.
Well,
Using theorem 311.
using theorem 311. The sum of two. Well, then we can label. Well,
Okay.
No, well, we don't have to. It can be.
Well, if we like numbers, we'll put that as what, 3 and 4? Okay, I labeled.
So then, and then.
I'm gonna label these 5, 6.
Yeah.
Okay.
So then, 2 plus 4 plus 6 equals 180. and then 1 plus 3 plus 5 equals 180, and then you can substitute, and then you already have those.
We got these two, then you still have to say
And
the
then-
measure of angle.
And then you can subtract.
Exactly. That's what they did as well too, which I thought was pretty cool. All right, that will work. But certainly calling out 311 or corollary 1 to 311 is way quicker.
Well, all you have to do is see.
By the way, that is how we prove corollary 1 as well too, is what you just did. Okay, so here comes the last thing of the day. This is new. Yeah, this one's pretty big. Pretty big.
You are cute cat.
All right, we're going to write a definition down first. I'll leave it to you whether you want to put it in your book of truth or you're like, I'll just write it down. I'll remember this. Okay, so we got a triangle, right? And triangles have 3 angles, right?
Right.
What would we call these angles? And I'm not looking for a cute or obtuse. What would we call those angles?
Angles of
We got to give them a new name.
Triangle angle.
Triangle angles would be cool, yeah. Yeah, they all add up to 180, then they're supplementary of some sort, but technically we define supplementary angle as 2 angles add up to 180, but I'm with you, I like that. Where are those angles in relationship to the triangle?
Inside. Interior angles.
Yeah, we're going to call them interior angles.
And then there's also exterior angles.
So if there's interior angles, there must be exterior. So where would be the exterior angles?
On the outside of 1, 2, and 3.
So here's how you create exterior angles. You go to any one of the sides and you extend it. So I'm going to go to any one of the sides and extend it. See what I did? And then I'm going to label that as what, 4, I guess. So 4 is an exterior angle.
Well, wait. Couldn't you also just draw?
I could do it the other way as well too.
Yeah, I mean.
So we're going to define this as the exterior angle of the triangle. And this is by definition. Remember, when I make a definition, it's because I said so. So I know what you were thinking, Jack. You were probably thinking about, this is called a reflex angle. This angle from here to here.
Yeah, that's. Yeah.
Okay. This book never talks about that. They're called reflex angles. Some of the worksheets I have use that fact. But this is a definition. So I don't prove this. I just state this. We will define an exterior angle to a triangle as if you extend one of the sides, the angle that's formed, it's not 180 degrees. Right? Because clearly there's an angle right here as well, that's 180. Right? We're talking about this one. Okay, so that's an exterior angle. So let's see. If this is an exterior angle, we call this a what?
Interior.
Call that interior angle. We're going to give 2 and 3 special names. They're the ones that are opposite
The opposite interior.
the interior angle 1.
Opposite interior angle.
That would be a good name. They didn't use that.
Open interior.
What?
Open interior.
That would be okay. They call them the remote interior angles.
Oh, wow.
Actually, I have a question.
Yeah.
If a line is a 180-degree angle, is a point a 360?
Remember, point has no size, no shape. It's just a location, so it has none of that. Yeah, but remember, that's because you're drawing it with a circle. I could have drawn a teddy bear, and that's my point.
But there's no way in the universe that
Well, a
everything
teddy bear
never.
will have a circle around
But a
it.
teddy bear is not the shape of the point. It's just it's a sit-in for a location.
Wait, that brings up problems.
Let's not get off too track. This is important. We've got to stick with this one. Okay,
The solar system.
so hold on, McKinley. So we got the exterior angle, and then not the one that's next to it, adjacent to it, but the other 2 are called the remote interior angles.
The exterior angle is
But wait a minute, right? But we don't have to draw the line right here. We could have drawn it right here. So if I draw it right there, well, here is your, okay, and then these 2 would be your remote interior angles. So don't get hung up on, it's always this number or that number. It's the 2 angles that are opposite the adjacent angle to the exterior angle. Does that make sense? So if I drew this one in this direction, come here, you. That's the, and these 2 are the,
remote interior.
is that something you can remember?
Yes.
Do you need to draw it or no?
No.
We're going to use this a lot. I don't mean like every proof or something like that. We're going to use this a lot.
Oh, yeah. Perfect.
Okay, so there, I drew it 3 different ways, and now we're going to do a proof. Okay. Can you see the exterior angle?
Yes.
Which one is it?
4,
Can you see the remote interior angles?
1 and 2.
I'm going to prove that 4 is equal to 1 plus 2.
Yeah, makes sense.
And that, hopefully no one heard that. I'm going to prove that the measure of angle 4 is equal to the measure of angle 1 plus the measure of angle 2.
Oh.
Somebody's going to hear the thing and like, did he just say 4 is equal to 1 plus 2?
That was a math mistake.
Okay, so I'm going to prove that the exterior angle is equal to two remotes added together. Okay. What do we got for a given?
ABC.
It's just a triangle. It doesn't say right of two scaling, isosceles, equilateral, equal angle. It doesn't say it. It just says you got a triangle. So this will apply to all triangles as long as it's in Euclidean geometry, plane geometry. Okay. Where in the world are we going to go? Somehow we got to get down to that sucker right there.
That so triangle.
So since you haven't looked at your book since I told you not to, so you get the first one. What do you see up there? Tell me anything you see that's true.
Angle 3 and angle 4 are supplementary.
Why? Yeah, no. Yes or no? He said because they're on a straight line. Yes, no? Arguments? Well, I agree with that. Sure, they make a straight line. 180 degrees. There's a statement. Jack, what else do you see up there? I can think of one other thing we could say.
1 + 2 + 3 equals 180.
Yes? Okay, we'll make those two statements. There's Jack's statement, right? That's Theorem 311. And here's Ali's statement. That's, I gave you the term yesterday. Do you remember? I said whenever we see two angles that make a line, we're going to call them a linear pair. A pair of angles. And what if it was three? Okay, then I say definition of a straight line. But linear pair is just really quickly easy to write than two angles, two adjacent angles that form a line. You know,
Applies to 4.
yeah, okay, I don't like that one because it doesn't specifically say they equal 180. It just says that the two angles equal the larger one. I want something that specifically says it's 180. And although I know the book used that, I disagree with the book on that one. Okay, we've seen this technique. McKinley, you're up. We've seen this technique probably, I don't know, 8 out of 10 times that we've done a proof. What's the next step?
Substitution.
What are we substituting?
1 and 2. No, wait, 2 and 1. No, 2 plus 4. Yes, yes.
None of that.
None of that. It's 1 and 3. No, wait. One of them.
What are we substituting?
Oh, measurement 1 plus 2 plus 3 equals measurement 3 plus 4.
Okay, you got that. This is, I mean, I'm saying we use this so often. I have two statements that say they both equal the same numbers, set them equal to each other.
When you take another substitution, you get the
Hold on there.
Not substitution.
Not
Wrong
substitution.
words.
All right. Does this now look like this?
No, close. It's getting
What's the
close.
difference?
You just have to subtract 3 and 3 together.
Ooh,
There.
pretty obvious,
Like-
right?
like
So what's
Jack
the
said.
statement?
Yeah, 3 is equal to 3.
Not substitution.
Subtraction.
Yeah, the book would have a reflexive statement in there. It would say 3 is equal to 3 and then do subtraction. I choose not to do that one because I'm just going to claim right here, it's got an equal sign. These are numbers, although they're letters and representations of angles, they're numbers. M angle 3 is a number. I don't know what the number is, but it's a number. So if on one side of the equation you have the same thing, I can subtract that without making a silly, you know, angle 3 is equal to angle 3 reflexive statement. But my math teacher would have told me I was wrong. Okay. Now that I'm the math teacher, I can make my own rules. All right. Cool? QED. What did we prove, by the way?
That geometry is.
No, what did we prove?
We proved that exterior angles are equal to 2 remote angles combined.
The sum of two remote interior angles. That's what we proved. This is 312. 312 says that the exterior angle is equal to the sum of the two interior angles. And remote interior angles, I should say. Ben, you with me?
Yes, I'm with you.
Yeah, this is a very important one.
Aren't they all important though?
Important in the sense that we will use this often. Nearly everything we do from now on is going to have a triangle in it. And then therefore, you know, we're going to use that Theorem 311, 180. We're going to use this sucker. Hey, sometimes we'll have auxiliary lines. We'll get vertical angles. Sometimes we'll draw an auxiliary line that's parallel to the bottom. We'll get alternate interior angles. You'll see. You'll see. Oh, you'll see.
This is where triangle.
This is where triangles begin, and it doesn't stop. And also, trigonometry next year,
Triangles.
actually, pre-calc is more. You're going to do a little bit of trig next year, but
I
not
thought we were
much.
doing algebra too.
You're doing algebra too, but we'll do a little bit of trig. But pre-calculus is it's all trigonometry
And then
almost.
junior year is
No, pre-calc is junior.
So then, senior year we'll do trigonometry.
Calculus.
Calculus.
Yeah.
So.
we're ahead of the game.
We're ahead of the game. Yes.
Okay.
I can pass a college.
This question is given in 3 different flavors,
Oh no.
right? Here's the first flavor. This is the easiest one. So vanilla. They're going to give you a triangle. They're going to give you one exterior angle, and there's going to be either a variable or a question mark. Check it out. There's no variables here. There's just numbers. Okay. So you got to put in a variable. So what's the equation? This sometimes it's hard to see, especially when this is really small right here. UT is really small, and they look really right next to each other. So just be careful. But that is correct. That's the equation. Could you solve that one? Obviously.
Yes.
Okay. And you are solving for a degree. I'm not solving for x. I'm solving for a degree. So there's your first flavor. One more. What do we do?
Figure out what the
So tell me, McKinley, what's the equation?
80 plus 70 equals question mark.
Okay. I'm going to use an x. Therefore, x is equal to.
A big number.
And what's the units?
150
What's the units?
Degrees.
degrees.
Okay. So there's the vanilla flavor. All right. The what's the medium flavor going to be? Now, what's the medium flavor?
It's going to be X and Y.
No, what's the medium flavor?
Chocolate.
Chocolate? Okay. So here comes chocolate.
What?
It's the same problem.
I was right.
It's the same problem, except I'm going to throw in variables.
Okay, so 3x.
So notice there are more variables than there are numbers.
3x plus 8x plus.
Whoa, Euro. Slow down there. Where's the remote? Where's the exterior angle first?
R3Z.
What?
R and Z are the exterior.
Yeah, well, tell me how big it is.
It's 8 plus 19.
8x plus 19 equals.
3x minus 6.
Keep talking.
Which is what?
No.
Which you solve.
Keep talking.
Which
You didn't finish the equation.
you put x on one
No,
side.
no. Back up.
3x,
Take a deep breath. Back up. Tell me what the theorem says.
Theorem.
312.
The measure of the exterior angle of a triangle is equal to the sum of 2 or more remote.
You gave me 1. Now try it again.
So 85 plus x.
Take a deep breath and back up and do it right this time.
8x plus 19 plus 3x minus 6. No, equals 3x minus 6. Which gets you.
You're
x.
slow. You did it again. The exterior angle is equal to the sum of the 2 remote interior angles.
So it's 3x minus 6 plus 85.
Thank you. All right. What do we do?
We do numbers.
Subtract 19.
Yes. No, wait, you put 3x on one side.
I would probably do the 85 and the -6 first.
So that's.
Now, your ways, I mean, I'm not arguing that you were with.
79 and then you get 60. So
Oh, I'm not sure why I did that. Now what?
60. 8x equals 3x.
I would get the 3x to the other side. And then, so that gives me,
60.
therefore, 12. Okay. Cool? So this is your chocolate flavor where they have you solve for x. Did we ever figure out how big any of the angles are other than 85?
Nope.
So this is the chocolate flavor. You're not actually figuring out how big it is. You're just solving for x. Me personally, I don't like this. It's not really geometry. It's just an algebra problem. Me, tell me how big that angle is. We'll call that the strawberry flavor. All right, one more. McKinley, redeem yourself. What's the equation?
10x plus 8 plus 4x minus 4 equals 130.
You got this.
Yay.
All right, Anna, solve that for me.
That would be 14x, and then 130 minus 4, so 126, and then divide 126 by 14.
Take a guess,
Which is 13.
which is not 13.
No, not 13.
3 times
21.
4 is 12, not 6.
Oh, so it's
Take a guess.
4.
4. It's got either got a 4 in it or it's got to have a
2.
What times 4 gives me a 6?
Uh,
4 times 4 gives me a 6. What other number gives me a 6?
8.
8 times 4 is 32. Gives
Oh,
me
right.
2. What other number gives me a 6?
Oh.
With a 9. With a,
9.
this is the answer. Darn it.
30, 16, 22,
It's got to be 9.
9.
Right? 9 times 4 is 6, right? All right. So this is your strawberry flavor. So notice, see the question? It says, this is your classic math teacher, math student joke. All right. Find a measure of angle C, and somebody says,
Circle C.
here it is. All right. No, they're asking you to find the measure of angle C. All right. Go for it. Tell me what to do.
20x plus 5 equals 4x plus 7 plus 7.
Okay. Can you solve that? Go, Jack.
Okay. What I would do first is subtract 4x. Oh no, 117, and then we do the subtracting of the 4x is 16x plus 5 equals 117, and then we subtract 5 is 112, and then x
We
equals.
did it again. Well, I just gave you the answer.
Thank
Yay, we're done, right?
No.
No, we're not
Wait,
done.
that means C must be 7. There, I solved it.
That means C is 7?
Yeah, no, X is 7.
That means C is.
So how big is C?
4 times 7 plus 7.
Yes,
Which is
35.
what?
35, I think. I don't know.
Yes, 35.
All right. So there's your strawberry flavor.
That was more like.
So let's see. Vanilla was, they're going to give you no variables. They're going to give you the numbers. Chocolate was, you solve for X, and then strawberry is you actually figure out. For me, I'm okay with vanilla and strawberry. Chocolate, not so much, although I do like chocolate.
I like mints better.
Mints?
Yeah, mints.
Really? So if I gave you a choice between
I don't like chocolate.
a chocolate shake and a mint, you'd choose the mint.
Yeah,
Okay.
if you give me the choice between the chocolate bar and a bologna sandwich, I'll take the bologna
Oh,
sandwich.
I'm with you. I'm with you on that. I'm a more of a savory person than I am a sweet
Well, I
person.
just don't like chocolate. Like if you give me anything and chocolate, I would pick the other.
You hate chocolate or you just don't prefer it?
I just don't like chocolate.
Oh,
Well,
okay.
not anything.
McKinley, bring chocolate cupcakes tomorrow. That way we can have more.
No. I know. I just said something.
Interesting enough, you know the history of chocolate?
No.
Where it came from? Anybody?
From the whole.
Chocolate came from South America.
Yes.
So let's see, either Mayans or Incas, I'm not sure which one of the two. It comes from the cacao plant, and there's these huge bean pods. And so they take these things and they cut them open. There's little like kidney beans, they're white. And they lay them out in the sun and they bake them in the sun. If you eat these things, have you guys ever had baker's chocolate?
Yeah.
What does it taste like?
It's like bad chocolate.
It tastes like, oh my God, what is this? Why would anybody ever eat this? So the magic is if you take cacao beans and you mix them with sugar, and then it turns into this magical treat called chocolate. And yeah, it was no chocolate did not exist in Europe until the conquistadors came to South America.
No wonder the Middle Ages was so dark.
So let's see. We gave them horses and smallpox, or no, we gave them horses and diseases, and they gave us chocolate and tomatoes. It was a pretty good deal.
Pretty good.
I don't like either of those things.
Because we didn't have tomatoes either. That came from South America.
Tomatoes. We didn't have tomatoes.
We didn't have tomatoes. So when you think about Italy and spaghetti and tomato sauce, it didn't exist.
No, it was only the spaghetti. Oh well.
Yeah, and spaghetti came from
Oh,
Yeah.
it came from
China.
China. Yes,
I know.
China.
I like things
Go
with
figure.
chocolate.
So Italy is just a lie. Oh,
Italy knows how to put good things together, right? But they did give us the Renaissance. So. I do. All right, get out of here, you villains.
You know how much I was
Are you okay? I'm doing a YouTube for them because, and then
All right, on to history class 3.3.
History class 3.3. Yeah.
apparently
Yeah, it's you didn't buy
three
it.
friends are not able to see.
You know, I had the same thing. Dr. K came and talked to me.
I realized like
So I have to figure out the DC chart and then we'll- All right, Ben, any questions?
No, no questions.
You not see yourself?
What? What are you talking?
He sees himself in the camera.
Oh, it's not being recorded. Ben, any questions?
No, no questions.
I got shoved.
All right, I will catch you tomorrow.